Morning, everybody.
Good morning.
Day four. Welcome to RNA Structure and Transcription. But before we get started, for those of you that are here on time, we're so happy for that. We're so happy to see you. Oh, I always can't turn that off before it starts. So happy to see you. And we have a special guest for you to start things off. Welcome, Mr.
Hey, what's up, everybody? How you doing, guys? Hey, it's pretty awesome. If you are on time, that's awesome to be doing this. Unfortunately, I'm still stuck at home because my kids can't use internet. So, yeah, so we're trying different ways of still getting some curriculum across. But this is awesome. I've been seeing not only Mr. Suter and Miss Smith, but Miss Christ as well, doing the Spanish and
French
the lessons for the day, the French for the day. So that's pretty cool. Guys, keep up the good work. Keep it rolling. Get your education in. And it was just, I'm glad I was able to stop in and say hi.
So just to show Mr. Koschel how smart you are and how much you're learning, I'm going to ask you a question of the day, and we'll let you put the answers down in the chat. I believe he can see the chat here on the side of what he's looking at. So we've been talking about DNA replication. And when DNA replicates, we get two new strands of DNA that are exactly the same, and each new strand has one piece of old DNA and one piece of new DNA. And we have a name for that. What do we call that? What type of replication is it? So in the chat room, could you tell Mr. Koschel what kind of replication that is? The Office. Abby said The Office.
Yeah, I left Pam at school. She's sitting in there by herself.
Haley Funkin first with semi-conservative. I think she was first. Here we go.
Yeah, I think so. Yep.
Awesome. See, look at that, Mr. Koschel. How many of these people? And Zulika asked about what about the people that were early. And yes, we're very impressed with the people that were early. There was people a half hour, an hour ago waiting in this room for it to start. So everybody say thank you to Mr. Koschel for popping in.
Guys, hey, great job, man. I'm proud of you guys. That's awesome. And we will talk to you later on then.
All right, Mr. Koschel, have a wonderful day.
All right, thanks. See you guys.
How awesome is that? See, people love you guys. All right, so let's get into this. RNA structure and transcription. And so today I'm going to start, and we're going to talk about RNA structure. Then we're going to turn it over to Mrs. Smith. She's going to talk a little bit about replication. So I need to show you my screen here. There it is. And you don't want to see that. You want to see that. So we have a new molecule. We've been talking about DNA. Can anybody tell me where we find DNA? Where's DNA located in the cell? It should be pretty easy, right? God has left. So I'm seeing people say the nucleus, and I think Abby was first right there with the nucleus. So yeah, Abby and everybody else, Extra Cheese and Jessica and Anna and Abby. We didn't do a roll call. Who else do we have? Donald Trump, big boy, is back. Diana's back. Elijah, Haley. Michael Jackson is in the house. Ow! Darius, Jake, Hannah Church, Maya, Mark, William, Mr. Hatfield, Jeffy Jeff. Look at there's a lot of people commenting. Dominic Lopez, Darius. Did I miss anybody? Aiden. Mrs. Smith, do you remember Romper Room? I always think of Romper Room when we're doing this. So, all right. So, yeah, everybody said that we're in the nucleus, which is awesome. That's where we are. So, here's the problem, and here's why we're talking about RNA and why we need another molecule. Because, like you said, DNA is in the nucleus and it can't leave, right? So if it can't leave, what are we going to do? Like how's the cell going to do what it needs to do? Because it needs to know what the DNA says. The DNA is the blueprints. It's the instructions. How do we get that message from the DNA out to the cell? And so when I think about that, I think about you guys sitting in class, sitting isolated at home, right? We're social distancing. How do we get the message out? How do we tell people what we need to tell them? And we do that through things like Snapchat and Instagram, instant messenger, our text messaging, all of those things. So how do we do it? We send a message out. And so DNA does the same thing. Your cells do the same thing. We have the DNA, we got to send a message out, and we send that message out using a molecule called RNA, which is a nucleic acid, right? So it's one of those nucleic acids. So what's the difference? Mrs. Smith and I both posted in our Moodle a worksheet called DNA and I forget what it's called exactly, but it's like DNA and RNA graphic organizer. There is no, you do not have to do that, but if you have Moodle open and you want to open that sheet and take some notes as you're going, some people like to write things down. That would be really helpful on what you're going to have to do tomorrow. If you like to just sit back and listen and try and take it in, do that. You can always come back and watch this again if you need to for the thing that you're going to do tomorrow too. So either take notes, don't take notes, however, whatever works for you. So here it is, the comparison. What is the difference between DNA and RNA? And if you look at this slide that I have up, DNA looks very similar to RNA. It's made of nucleotides. So what's similar? They're both made of nucleotides. But there is some really minor differences. So DNA is deoxyribonucleic acid. RNA is ribose nucleic acid. So the deoxyribose sugar in DNA is exchanged with a ribose sugar in RNA. And if we look at this, I think I can get like a little pointer. If we look right here, so we know this is our sugar molecule. There's our oxygen. There's our 5-carbon sugar, right? If we look right here, that H in DNA is replaced with an OH in RNA. And that's what makes that sugar different. So it's kind of minor, right? It's kind of minor, but it is a difference. Over here, so we have our base, our sugar, and our phosphate group. Over here, this is a thymine, and we see this little branch coming off, and there'd be a molecule here. We don't really need to get that deep into it, but if we look over here, there's none. And so thymine gets replaced with a new base called uracil. So really, if you think about it, everything's the same as far as the nucleotide goes. It's a sugar, a base, and a phosphate group. But we've changed one of the bases, and we've changed one of the groups on the sugar to be an OH. So let's back out a little bit, look at the whole molecule, right? So DNA is a double helix. We've been talking about that. It's a 2-stranded molecule. RNA, 1-stranded molecule. Single-stranded. All right, so there's only one side to RNA. We have adenine, guanine, thymine, and cytosine. These are our 4 bases that make up DNA. If you look on the other side, same thing, right? Adenine, guanine, cytosine, but now we change thymine to uracil. And so notice something. Thymine is a, oops, I don't want that up. It just covered up what you guys are supposed to be looking at. Thymine is 1 single ring. Uracil is 1 single ring, same thing. So if we think back to like, oh, that whole pyrimidine and purine thing, can we remember what they are? Purines, P-U, G-A, PUGA2. So the guanine and the adenine are purine, and the pyrimidines then would be the thymine and the cytosine, right? So really, uracil is going to fall into that. It makes sense that it would replace, since it's a single ring, it would replace the thymine, if that makes sense. More than we need to know, but that's the thing. So major differences, a different base, a different sugar, single-stranded. Let's keep going. There's 3 types of RNA. So we're going to do a little previewing here. So we're talking about RNA, learning about that for the first time, but let's do a little previewing. We're talking about structure versus function. Okay. And I think, I didn't say that right. anytime we talk about anything in biology, we always put structure and function together. So I think if we think about the 3 types of DNA of RNA and keep structure and function in mind, it might make more sense to you. What am I talking about here? There's 3 types of RNA. There's messenger RNA, ribosomal RNA, and transfer RNA. All 3 of them are made in the nucleus because that's where the DNA is. So we're using the DNA to make these. All 3 of them leave the nucleus, go out to the cytoplasm, and perform a job. So what kind of job? Messenger RNA performs the job of carrying a message. And it's laid out in this single strand that makes it really easy to do that, right? Really easy to read it. Ribosomal RNA is the ribosome. So when we've talked about ribosomes all year, what we're really talking about is kind of this ball of RNA. And we could really get deep into it and things. We don't need to do that right now. And then transfer RNA is another type of RNA that's kind of folded up on itself in a unique way. It almost looks like a T if you think about it. And it carries an amino acid. And so now a big question for you in the chat. If transfer RNA carries an amino acid, and we would get a bunch of those together and put those amino acids together, what organic molecule would we make? And this is why we did this in the beginning of the year, so this stuff makes sense. I saw Mrs. Smith's eyebrows go up where she's waiting to see if you guys get the right answer. I can tell. I know that look. What molecule do we make if we put a bunch of amino acids together? So giving it up to Jeffy Jeff here with his answer of amino acid or protein. I'm sorry. Things weren't working the way I wanted to. I think Jeffy Jeff was first one in. So good job. Yeah, so we make a protein. So if you think about what we're doing and what we're learning here, we have DNA, we have a code, we're going to send a message out of the nucleus, out to the cytoplasm, and eventually that message is going to be turned into a protein. And we're getting ahead of ourselves, but it's okay. So just to get ahead of ourselves one more time, now I'm out in the cytoplasm. We see a ribosome, so we know a ribosome is probably located on the ER, but maybe floating around. Here's a messenger RNA that we made, and Mrs. Smith is going to show us how to make this messenger RNA. Here, hold on a second. We're getting a call. Should we answer it?
Hello? Hello?
Oh, I hung up. I think that was like a real, I thought it was a robocall. So we're getting this real RNA. I bet that was funny. Messenger RNA goes through the ribosomal RNA. It's reading it. And these transfer RNAs we were talking about are carrying those amino acids over and putting them together. And we're going to talk about that very shortly, but not today. All right, Mrs. Smith, I'm going to turn it over to you. There was one other thing I want to do, but I'll turn it over to you for a minute. I'll let you do transcription.
Okay. All right. So you need to make me big. Oh, he's going to walk away. No, I can't do it. Suitor, come back. Make me big. Make me big. Thank you. Sorry, guys. All right. So, all right, I'm trying to calm down. Our antics.
Well, yeah, it was Mrs. Houck trying to call. I thought it was the robocall from Mr. Scola, because Dr. Scola, he said he was to send out a call, and I thought we could listen to it together. And then it was Mrs. Houck on the other end of the line, and it's all recorded for posterity. And then she called me and back.
All right.
But we're good now. See,
Okay.
this is why you tune in. It's free entertainment while you're social distancing.
All right, I can't even think. All right, let's start off with DNA. Okay, so I drew my little DNA here again on my infamous whiteboard, which, by the way, I'm trying to get a bigger one. We'll see if it actually comes, if Amazon comes through, if it's considered an essential for a bigger whiteboard. So when we're looking here, okay, first we're going to start off, and I want us to label which side is 3' and which side is 5'. on our DNA. So up here where the phosphate is on this side, is that going to be 3', 5'? What is it going to be? Up here at the phosphate. Haley, good job. Okay, 5' at the top. Good. Remember that it's high 5. Okay, so it's 5' on that side, which means that down at the bottom, that's going to be 3. Good. Okay, and then so if it's anti-parallel on the other portion over here, it's going to be what on this side? 3. Good. Okay, so we're going to have 3' at the top here and then 5' at the bottom. Great. You guys are doing awesome getting this information. Okay, so that's labeling our regular DNA. You can see I use the base pair rules. So if this one's going to be A, this one's paired with T, G with C, A with T, C with G, same as before. Now we're going to kind of go into, instead of, and sorry, I see that there's a little bit of light coming through my window. Instead of going into now replicating DNA, so we no longer want an exact copy. We want that message that's going to be going through, like Mr. Suter said, is going to actually then be able to eventually make a protein. So at this point, DNA is still where? Where is DNA located? Waiting to see for where DNA is located. I think I'm live. In the nucleus. Great. Okay, so we are in the nucleus still. So I want you to remember that. Okay, DNA doesn't leave the nucleus, which means when we start talking about the transcription process, transcription has to also occur in the nucleus. Okay, so transcription also occurs in the nucleus. When we deal with transcription, we still need to open up the DNA. We're still talking about opening DNA in order to write the message. So there's an enzyme, the same as DNA replication, that's going to be coming in and opening up the DNA. So if we want our DNA to be opened, we need to, again, have an enzyme that's going to be able to open DNA. So it's going to open the helix. Great, helicase. Okay, so we've got our DNA helicase. Okay, that is still going to open up the DNA. So at this point, DNA helicase is going to open up. But instead of using that semi-conservative process and actually rewriting DNA, we're now going to be using a different enzyme because we want to write RNA. So if when we write DNA, we use DNA polymerase, can anybody guess what enzyme we're going to use when we're making RNA? And I'll give you a second while I am opening my DNA here. Okay, good. Okay, so we're going to use RNA polymerase. So what I did quickly while I was waiting for that, I went and I used my DNA helicase and opened up my DNA. Okay, so now DNA helicase is gone. So RNA polymerase wants to come through. if you remember what I talked about with reading with DNA polymerase, it is still the same with RNA polymerase. So which strand is it going to read if RNA polymerase is at the top? Okay, so now we have the RNA polymerase. Which one is it going to read? Is it going to read this one? So we'll call this A, or is it going to read this one? We'll call B. So we're going to start here on the 5' side, or we're going to start over here with the 3' side. What do you think? Just like DNA polymerase.
Because we want to be on the leading strand, right?
Okay, I got mixed things here, but Alexi is the first one that's got it right. It's going to read on this side, it's going to read from 3 to 5, and it's going to lay down 5 to 3. So it's not going to read this side. It's going to read this side. Okay, so as RNA polymerase comes down, then it's going to lay down RNA nucleotide. So this is no longer a deoxyribose sugar. This is now just a ribose sugar, and we have to match the bases. So if that is a T base, what base then are we going to match? If that's a T base, what are we going to use? Oops, marker switch. So if it's T, T matches with A. Good, Haley. Okay, so we got our A. Oops, forgot our low phosphate. The next one then, it's going to lay down again here, and it's going to be able to connect to our message, and it's going to lay down another base. So if it's C, it's going to match with G. And so then it's going to continue to lay down new nucleotides with, again, ribose sugar. I tried to draw with a different color, but it's not the best. Okay, so I got to an A. What am I going to do once I get to an A? Because there's no thymine in RNA. There's no thymine in RNA. So what am I going to lay down? Well, I can't lay down another adenine. Good, Annie. Okay, I have to lay down that U, that uracil. Okay, I know you've heard uracil before. So uracil is going to be what's replaced in that RNA. That's like the secret message. Okay, when you're sending text message snaps, etc., and you want to send that secret code or the emoji or whatever that is representing something else. So the secret code for RNA is that uracil. Okay, and then for the last one, I've got a G. And so then that's going to be paired with the C. Now, in RNA transcription, once we've made RNA, this is not the new DNA. This idea of this producing this doesn't stay. This will actually now leave the DNA. And I wish I had an animator, but I don't. Okay, so this leaves. And that's going to leave. And then for the sake of saving time, I'm not going to draw it back together, but these will then create its little hydrogen bonds between it again. And if you'll notice, I'm being very careful to draw 2 bonds in between the adenine and thymine and 3 bonds in between the guanine and cytosine. And so the DNA will go back together, and the RNA is now that it's in a secret message, okay, and it has created this RNA or mRNA, messenger RNA. This can now leave the nucleus. Quarantine has been lifted for the mRNA, and it gets to leave the nucleus. Okay? It gets to leave the nucleus. And so mRNA is going to leave the nucleus. So when we're talking about transcription, okay, and we're talking about that idea, remember that transcription, if you think about scribing or scripting, so if you weren't here when Mr. Koshal was here, I think it was pretty, point on to have Mr. Koshal here this morning, since he is the English, talks about writing to you. So we're talking about writing RNA. We're writing in a new language. And so we go from DNA language to RNA language, and we use the ribose sugars. We use the uracil instead, and so then it'll leave. So again, remember, if you see a T, though, this is the most common mistake. People see a T and they start writing U. They're still adenine, so you're still going to have an A pair with the T. It's just that down with the A, you would pair the A with the U. So if we needed to read this side, then it would have to be read. It would have to open up DNA on this side. So the helicase would come over here and open it up, and then it would read the message in this direction from 3' to 5'. Okay, so that's a quick little overview of transcription for you using my little whiteboard. Did I get everything, Mr. Suter?
Yes, that was awesome. How about round of applause for Mrs. Smith? That was an awesome job. I'm blown away, Mrs. Smith. Every time we ask a question, they're on it. They're on it. I'm blown away. So I have one last little thing. I'm sorry about the phone call. I got me all screwed up. But one last little thing that I wanted just to point out. This is the mind-blown minute of the day. Because it's like one of those things that it was a mind-blowing experience for me when I first learned about it. So I'm going to switch my camera real quick here and just show you something. And as I'm doing that, during the Romper Room shout out, I got a text message while Mrs. Smith was talking from my wife, who apparently was in there and told us that we were late getting started and was mad that I didn't mention her during Romper Room shout out. So a shout out to my wife, who is working from home upstairs right now. All right. Mind-blowing minute of the day. So we are talking about a cell. I want you to picture this piece of paper as a cell. The whole piece of paper is a cell. And right here in the middle, I'm going to draw a nucleus. Here's my nucleus. Can we see that? I think we can see that. And so in the nucleus, we have DNA. Now, you have to remember the DNA is all opened up and spread out, right? So we have this long piece of DNA all opened up and spread out so we can read it and write stuff. There's a section of that DNA that makes ribosomes. And I'm just going to say that it's from right here to right here that's making ribosomes. And actually, there's probably more than one. And a lot of times my understanding of this is that the DNA might wrap back around through that same area. But everywhere there's a piece of DNA that makes ribosomes ends up in about the same area of the cell. Well, that's not really that big of a deal, you might say. But imagine we have a whole bunch of pieces of DNA. So if I draw a couple pieces of DNA and make sure I wrap it back through that area that makes where the ribosomes are made, right? So we're going to keep doing that. All right. So whole bunches of pieces of DNA, and everything in this area, all the ribosomes are made in that area. Now, I want you to picture something. Ribosomes are being made. So ribosomes are these little pieces of RNA that are all balled up, right? So let me draw in a whole bunch of ribosomes being made. All right, so I'm drawing a whole bunch of ribosomes being made too. So just a whole bunch of little circles there, you can see. All right, now, if I showed you this picture 3 months ago and I said, this is a picture of a nucleus, and I asked you what this dark dot was in the middle, what would you have said? Oh, Mrs. Houck, it's not your fault. I should just have ignored the phone call. But I got excited for news. You know how it is. What is that little dark spot in the middle of the nucleus? Yes, Jeffy Jeff with the nucleolus. So, yeah. So here's the thing. Here's the mind-blown minute, if you ask me. When we get through with DNA, we're going to start talking about cell reproduction. And when we talk about cell reproduction, we're going to tell you how DNA will wrap up into a chromosome. So if I come back over here and show you my screen again, because I can, I show you my screen again and we just go to Google and I type in chromosome, if I could spell it, chromosome, and I go to image and I pull up a chromosome. So here is a good picture where we see a piece of DNA all wrapped up into a chromosome. I want you to now think about what I was showing you down here. If all that DNA wraps up and all those ribosomes leave and go out to the cell, to the cytoplasm, what happens to the nucleolus? It disappears. So for years, I was always taught the nucleolus just disappears. But it doesn't. It never really was there to begin with, if you think about it. And now you know, right? Because it's the parts of DNA that we're transcribing, and it's all the little ribosomes. So, mind-blowing minute of the day, if you ask me. Not a big deal, but I thought worth mentioning. So, what else? I think that's it. The only other thing that we had for you today is in Moodle, there is a quizzes quiz. So we thought it'd be cool to do a little competition, right? You're answering questions so well in the live streams. There's a quizzes quiz. If you go into quizzes and you, I love that stuff. You go into quizzes, there'll be a quiz in there, DNA and replication, I believe it's called. Take that quiz sometime between now and tomorrow. We'll announce the winner tomorrow in the live stream. And that's the only thing you have to do tonight, other than this. So we went a little bit longer than normal here today, but there's not as much to do. Just a quiz. I think it's like 20 questions. We'll see who wins.
Yeah, 20 questions.
Anything else, Mrs. Smith?
Oh, go Smith's class. Whee! And it's the same quizzes on my Moodle as his. So equal, same questions.
All right. So once again, like always, we appreciate you joining. Wash your hands. Stay at home. And thanks for keeping the learning going. Learning continues. Hashtag trailblazing and all that good stuff. We will see you tomorrow at 10:30. Same bat time, same bat channel.
And office hours today, if you need them.
Yeah, people keep popping in and out of the office hours, but never between 1 and 2, and I'm actually there.
Right.
Between 1 o'clock, guys. Office
2
hours.
o'clock for me. I'll be a little late today. I actually have a student that's scheduled a meeting with me at 2. So during the office hours.
Come and see us. All right. Love you. Have a great day.